I think Matt's already mentioned it, but I'm going to give the second part of the talk on more advanced neural network architectures, and that's going to cover some fundamental bits on CNNs, transformers, and GNNs. I guess some of you are familiar with some of these bits, so I'm going to just ask you to maybe for a show of hands, who's used CNNs before in the audience? Okay, so most of you. Transformers, okay, and GNNs, so graphs, okay. So there is, right, so that's just to gauge basically how much time I should spend on each of these sections, which is, yeah, it's some good information to have. Sorry, my voice is a bit fading because I just came down with something over the weekend, so hopefully you guys can hear me fine online, also at the back. Right, so I thought I'd begin with this slide, which is borrowed from a colleague of ours, Christian Lessig at ECM. So he's quite a big fan of this bitter lesson, which comes from, well, this website here from Rich Sutton. It basically says that the most important factors determining the performance of an algorithm, of a model, are how much compute and how much data you have available to throw at it. So it's not. So if you read this, you might think, okay, the design doesn't matter, but there's something hidden in there, which is this sensibly designed bit. So you have to have a sensible design model for this to make sense. And hopefully I'm going to convey upon you some ideas of what a sensibly designed model might mean in this context. What is a sensibly designed or a sensible design for a neural net? So it's basically, as Matt was saying, stuff that people have tried before and it worked. So you have a tried and tested combination of building blocks or architectures, and some of these will be the ones that I have mentioned. So CNNs, GNNs, and transformers. And what these do is they have specific things called inductive biases, and these encode some prior knowledge you might have about the problem at hand. Not too much, though. You don't want to build too much information into the model. So kind of like constrain or the model from the get-go towards this to favor a specific type of solution. But it also has to scale. So if you throw more compute, if you're GPU rich and happy, and you have lots of data, you want your model to be both hardware and data efficient. So you want it to scale. You don't want it to you don't want to lose compute, just waste compute and do nothing. But what you also want is good out of sample performance. So you want the model to generalize to data it hasn't seen before on the test data that Matthew was mentioning. So this is the game plan, and I'm going to mention some of the classic architectures of neural nets built upon these blocks, which would be deep convolutional networks, UNets, vision transformers, GNNs of the encoder, processor, decoder flavor, which is what AIFS and GraphCast and other models are based on. So I've included plenty of references for self-study in the slides towards the end. So there's like lots of links to various blog posts or notebooks or GitHub repos that you guys can use to get some model code to try things out and like get your hands dirty. I guess the easiest way to understand what these things do and what they do not do and what kind of like advantages and disadvantages each of them have is to go and try them yourself. Yeah, so first on CNNs, I guess I think all of you in the audience have raised their hand, or almost all of you have raised their hand when it comes to CNNs. So a CNN is just, I'm just going to go quickly through this. CNN is based on fundamentally on a convolution operation. So this comes from signal processing. A while, like tens of years ago, people have come up with these definitions. You're just basically using a sliding window to average the to average a signal locally in space or time. So you're essentially applying this local operation. So the convolution kernel f to your function g and getting some kind of like new signal from this. And you can see here in this number-heavy slide, this amounts to doing matrix multiplication. So you have like an object called an averaging kernel or a filter, and I'll justify the name in a bit, that basically does a weighted average of your input data. So in this case, the input data is just like a two-dimensional panel of numbers. You can think of this as an image, and then you're computing these local averages, and the result is going to be a 3 by 3 matrix, which has, or image, which has these the result of each local convolution operation in its elements, right? So why is this nice? Well, you can feed an image or a stack of images to the through a model. So the CNN is here on the right, and then you have a learnable weight matrix that basically encodes those filters, and the parameters of the filters are now learned themselves. So as part of the optimization procedure, and then you have something called an activation map, or the output of the network, which has which basically encodes some information about the average input image that you had of this nice dog here. You can compare this against the MLP. So Matt defined an MLP before. What the MLP does is essentially the same thing. It's just like you have a much bigger learnable weight matrix that has to map between the input image and the actual output. So in this case, the output here is a size 10 because I'm doing a classification task. So I'm basically mapping the input images to one specific class of image. So is this a dog? Is this a cat? Is this a deer? So I have like 10 different examples, 10 different classes of animals, and I want to see like which class does my input image belong to. And then you see like the difference in the size of the operators, and that's because an MLP doesn't have any weight sharing. So there's like you're learning an individual mapping operation for each pixel of the input image. So that's that will scale poorly with the image size. It's not translationally invariant or equivariant. So that means if you shift the dog in this image by a certain amount of pixels, with the MLP you'll get a different output signal, but with the convolution, the output signal is gonna stay the same. And you want it to stay the same. You want to encode this inductive bias of translational equivariance into the problem, because a dog, if you shift the image of a dog by a few pixels, it should still be a dog. So it's not it doesn't semantically change. Right. Again, as Matthew was showing, it's very easy to encode to implement these, and I think this is a major advantage of using these out-of-the-box convolution operators for something from a library like PyTorch. These are very fast, so you write Python, but what happens behind the hood is usually a CUDA kernel gets executed. So if you're running on a GPU, this means the code is going to be very fast and adapted to the hardware at hand. So you have, again, a big design space of things you can tweak in your convolution, which is the kernel size. So basically, this is the size of the averaging window. You're using the stride, how far you jump to get to the next averaging window, and so on. The padding, how many fake pixels or how many boundary pixels you use for the domain to compute the convolution, and so on. So there's a nice guide that shows you visually the effect of all of these options. This archive link that I put on the slide. Yeah. How do you build a deep CNN? You do two things. You stack convolution layers. As Matthew was showing, you can just do a sequential stacking of layers, and this means you're increasing the depth of the model, or you can increase the channel dimension. So let's say instead of mapping the image to like a single representation in the encoded space, then you can have it's shown here on the left side many channels with basically the same matrix operation. So you essentially add one dimension to this learnable weight matrix, which is the channel dimension. So for each channel, you're learning a different convolutional filter. So again, this is because it's all matrix multiplies. So it's all going to be very fast. So once you think dense linear algebra that's going to be super fast on GPUs. So that's a good thing to have in your neural network design. Okay. One important concept is that of the receptive field. So receptive field, what this essentially means is that if you look at a layer of the specific neural net and you choose a pixel in the image encoding in that layer, what is this pixel sensitive to? Which area of the input is this pixel sensitive to? And you can see that the size of the receptive field increases as you go to deeper and deeper layers. So, like in layer 3, you depend basically the red pixel depends on these 9 pixels in layer 2 because of the convolution operation. And if you recursively go back towards the input, then the size of the receptive field keeps increasing. So it means you're compressing more and more information as you make your layer basically deeper and deeper. And that's again a nice property to have because you're essentially building this latent representation of the image by just stacking CNN layers one on top of the other. And a layer, coming back to Matthew's slide again, the MLP, it's the same thing happening for convolutions as well. It's just like instead of having these the weight matrices, big chunky weight matrices that you have for MLP with no weight sharing, you have these thin learnable filters for the convolution operator, but then you have the same nonlinearity, which can be a ReLU or something else, and then optionally you might have something like a pooling operation. So pooling is just like a fancy word for averaging. So you can basically stack many of these layers and do something called feature extraction. And what this is basically you're getting useful information about an image. So this is something classic from before neural nets. People knew that applying something like a Sobol kernel would just give you the edges, would just give you the information about where the let's say the transition between various image features happens in a natural image. So you can see like the edges between the staircase and the sky. You can see the contours of people and so on. So by just applying this, which is a fixed filter, you can get basically this information. You can get some information about the structure, the semantic content of the image, and you can think, okay, if I don't fix this, guy, if I just learn a bunch of these guys, am I going to learn some useful information about the structures in my input images? And the answer is yes. And there's a bunch of nice websites showing this. I have some links at the end. But turns out if you stack many layers of a CNN, so various with various kernel sizes and various output sizes, so going from the size of the input image all the way to something very small, then what these intermediate layers are going to learn is basically various types of image features that various so these are latent features, and they correspond maybe to edges in an image like I've shown before, or maybe if you think about classifying dogs versus cats, it's cats noses versus dog noses, or eyes or heads or stuff like that. So your model is kind of like building this latent representation of image features that it's going to build its decision-making capabilities later on. So what happens in this kind of like tail of the network is basically the model decides how to classify dogs versus cats or versus ponies or versus something else based on these latent feature representations. Right, so if you put all of this together and you add a nice tweak that somebody came up with in circa 2016, I think, and it's a very famous paper. It's got 270K citations. So if you guys write a paper like this, then you're pretty much set. So it's called deep residual learning for image recognition. So it introduced the concept of ResNet, which is basically this. So stacking, you stack layers just as before, but then you add this bypass connection. So from the input all the way to the output. So this is called a residual block. And what this does is basically allows the optimization or the training procedure to optimize the network better, because the gradients during the backward pass, they flow from the loss to the weights much better because of these residual connections. So what this plot shows here is the status quo before the introduction of RESTnets and the status quo after. So basically what you noticed before is that if you kept adding layers up to some point, basically your model wouldn't be able to fit the data as well. So the 18-layer model is actually doing better than a deeper layer, than a 34-layer model, which is kind of like not what you'd expect. And once you add this connection, you see what your deeper network does much better than the previous layer. So the 18 one is now surpassed by the deeper net, and that's because of the gradient signal getting back propagated much more efficiently and much through the whole thing. Question for you guys. Can you make a guess what these drops in the error rates are corresponding to on these training curves? So basically, these are the training curves showing the behavior of the error with the iteration count. So going from 0 to like 50 times 10 to the power 4, so like 500,000 iterations, and the error decreases. And why do you think you have these jumps here? Yeah. So I got the answer from somebody in the back. Thank you. This is when you adjust. So you have, as Matthew was saying again, I keep quoting Matthew. It's as Matthew was saying, you can have a custom earning rate schedule. So what happens here after 15,000 iterations or 150,000 iterations, sorry, you adjust your earning rate. So you decrease the earning rate to, and then continue. So every time you adjust the earning rate, you basically, you have this jump in the error curve. So that's something you can also set up quite easily using PyTorch or TensorFlow, because they have these things built out of the box. Something called UNet. This was used for image segmentation, but it's also being used in diffusion models. So it's still an architecture that you guys should know about. What this does is basically so you feed it an image at the input, and then you build later representations of that image. You compress the data onto smaller and smaller latent space. But again, as before, you increase the feature dimensionality. So these are like, this is tall and skinny, and then this is small and chubby. Chubby meaning they're large in the feature dimension. And then you go back, you do the opposite on the way back, and you also have these residual connections that again allow the propagation of information to be more efficient both in the forward and the backward pass. So these things called the skip connections. And then you have the task here was image segmentation. So like what this means is that you identify, let's say, objects in an image. If you have like an image, a photo taken outside, well, somewhere on the freeway, you'd want to identify all the cars and all the trucks driving on the freeway. So that would be an example of the image segmentation task in action. Yep. And again, this is being used in diffusion models quite a lot these days. So it's something that pays to know about. When it comes to CNNs, you have many options for out-of-the-box models. One of them that I thought to mention was, which is because it's quite famous, is the Hugging Face repo. So some of you I'm sure have seen this. You have a lot of image models, both pre-trained and also code to build these models and train them on Hugging Face. And these are basically state-of-the-art vision models, both convolution and transformer-based. I'm going to talk about transformers in a second, but this is a useful link to have to go about and investigate these things by yourselves. Yeah. I'm moving to the second bit now, but any questions on CNNs? Or maybe I should take questions at the end? Yeah, any questions now, or Can skip. Okay. Yep. So yeah, the transformers and self-attention bit is the second main section of my talk. So I've included this slide to like tell you why should you care about these models. So these are older age nowadays. People use them for pretty much anything because they're very efficient. And I've included some examples of things that you can do with them. So you can generate high resolution images using, say, text prompts. And this is what Stable Diffusion does. You can use them to build chatbots or text generators like ChatGPT. You can use or large language models, DeepSeek, Claude, and so on. But you can also use them to build very efficient data-driven forecast models, and I've included all of the some of the major ones. Forecast.net is version 2 actually, so boys don't be upset because this is a typo. So yeah. It's but also Pangu Weather, AIFS, CRPS, GenCast. They all use some flavors of this. So yeah. Before I introduce what these things are, maybe I should say what's not so great about CNNs and recurrent nets, which I haven't actually defined, but maybe I'll just criticize them without actually saying what they are. Because that's always a good idea. Right, so CNNs, I remember I talked about this depth versus receptive field thing. So in CNNs, the information propagates kind of slowly. So you need to have a large receptive field because the kernels are usually small, like 3 by 3 or 5 by 5. If you have like a high resolution image, then you need to stack a bunch of layers before the receptive field is going to be large. So before you can start mixing information from like across large distances in an image. And also you don't have a lot of positional awareness unless you use specific embedding. So like you don't know anything about the relative positions of pixels in an image unless you specifically encode that in some smart way. But that can become less hardware efficient. So that can impose a penalty on the scalability of the model, which is not a good thing. Right, and RNNs, they basically what they do is like they apply the same operator sequentially. They have, which again doesn't scale to large data sets, and it's not hardware efficient. And you also have issues with propagating gradients through these recursive calls, and it's easy to forget things that you have learned because you keep like imagine this, like you're reading a book every day. You kind of like it's easy to forget what you've learned like a week ago because you can only store so much in your short-term memory. So that's what these things do. And I guess transformers coming out of Google were a very nice and hardware efficient idea to address some of these issues. And I'm just going to motivate them by using an example from language processing, language translation actually from English to French. So think about words as tokens, and you can think of tokens as being like a numerical abstraction to a word or chunks of words. In this case, it's just going to be a word for simplicity. But usually, in practice, what people do is like they take fractions of words and tokenize them, which means you go from like a string to a sequence of integers, essentially encoding information in the words. So you have two steps. You have the first step is the encoding step, which communicates information between representations of input language tokens. So you have like a bunch of English words that you want to translate to French. You encode the information first in the English sentence, and then you decode autoregressively by generating the French equivalent of your English sentence one token at a time, or one word at a time in this case. And you use all the information you have before. So basically, all the encoded information plus whatever you've decoded thus far. So once I've decoded my second French word, then I can use the first and the second French word to decode my third French word, and so on. So you build up information gradually as you do the decoding step, and this is what's essentially shown here. I arrived at D. First, you have mixing or communication of information across all of these tokens, which are the English language words. You build these gradually, these hidden layer representations of these this latent information, and then you use a special token, which is a start token. So you say to the model, I want to start translating, and then you do basically the decoding step. So from the latent representation of the encoded sentence plus whatever tokens you have, you build gradually the French translation. So, je suis arrivé chez whatever. Okay, that's, thank you. Okay, so, and then, yes, so, and then you have these embeddings that you build gradually, as I've said. Okay, so if you want a fancy image, this is it. This is from the Attention is All You Need paper. Again, 180K citations. So these guys are all very famous now. You have the inputs, the English words, and then you have this magic thing called a multi-head attention block, and then a feed-forward block. And then you pass information onto the decoder, and then the decoder actually, through this connection here, gets information from the encoding step, but it also gets information from the outputs. So from the whatever French words you have translated so far in an autoregressive fashion. And so you can see there's these two separate, kind of like conceptually separate pieces of this architecture, but they look very similar. So the magic happens here and here. So this is the communication step. This is where you exchange information between the tokens, and then this is the computation step. So this is where you mix information that you have exchanged. So now that I have all the information from my neighbors that I attend to, so that I pay attention to, then I mix this information and I build this latent representation of the English sentence, and I pass all the information to the decoder to do its magic. Right, and the magic of the attention operation is basically built on three separate abstractions: the queries, keys, and values, and the softmax operations. So the queries are basically the things that I'm looking for. So this is the keys are the things that I have, and then the values are the things that I will communicate. And then I do the attention. I do first a dot product between the queries and the keys. So this will basically highlight any queries that match the information I have. That is, the keys will be magnified by this. We'll have a high dot product. So this is how the dot product works. If the two vectors are aligned, then the dot product is big. And then the softmax just highlights with some normalization. It highlights the salient information, and you basically multiply that with a v so that you have the information that you communicate. So think about like this nice example. You're a student at ETH and you have like a homework to do, and then you go to the library and you have a bunch of items in your homework. These would be the queries, and then you have the keys, which are basically the tables of contents to all the books that you search, and then the values are the contents of these books. So first of all, you have to match whatever homework assignment you have to the table of contents. So you have to identify the books that are most relevant to your assignment, and then once you have done that, you're basically communicating to the teacher the contents of each of the books, hopefully in a nicer way, not just in a nice representation of that. So of course you can scale this to many. You can do something like something called a multi-head attention, which basically parallelizes this operation to across the what's called the head dimension. So you basically attend to many things at the same time. coming back to the example of the ETH homework, you have not just one homework in a single subject, but you have like 5 homeworks in 5 subjects you're taking, let's say, in the same semester, and you consult the same books. You have like applied math, you have partial differential equations, you have like ODs, you consult the same books. And the nice thing you can do in this case is that you can do all of these things in all of these lookup operations in parallel. So you can parallelize this across the head dimension, and because it's a matrix multiply, as I said, it means hardware efficient. So whenever you do like dense linear algebra, that's hardware efficient. Or there's ways to make it hardware efficient, and people have done this for you. So there's fast implementations of these operations available out of the box through PyTorch or TensorFlow. We use them all the time in AIFS. So yeah, it will be fast. Vision transformers. Just coming back to this. Okay, so I said encoding, decoding. What if you're not doing sentence translation, so you don't have 2 separate data domains? Then it turns out you can actually do a lot of things with just the encoding step. So this is what a vision transformer does. It basically does image tasks by just encoding patches in an image. So the tokens here are not words or not fractions of words, but are basically patches of an image. So you've got this nice building here that they split into patches, and then you have the individual patches being projected onto a latent space. You have something called a positional embedding that's added to this latent space representation, and you have the transformer encoder block, which is just as before. You have the fancy attention operation and the MLP at the end. Again, a stacked sequence of layers. So this is what this L means. You have L layers of essentially the same operation repeated. And then you have, at the very end, you have a network head that does whatever task you want it to. So in this case, it's a classification. You classify this as a building or something else. Maybe a question for you guys. What do you think this positional embedding is useful for? And I've shown this being used in the translation example before. Why do you think we need this thing? Right. So you want to encode a natural, at least in a sentence, words come in a specific sequence. So if I jumble the words around, the sentence doesn't make sense anymore. So you need to encode the specific sequence or the position of the one word relative to the other words in the sequence to give some model some information, to give the model some information about this. So this is why, yes, this is why we need these things. Yeah. So this is the idea. And again, you have a bunch of implementations available out of the box on Hugging Face, but also like this very nice example which comes from Jesper, a colleague of ours, ECM which has some notebooks that you guys can download and run and play around with all of these models and see what they can do for you. Right, any questions before I move to GNNs quickly now, or maybe at the end? No, am I on time? Am I okay? Yeah. Yeah, so GNNs. GNNs operate on graphs. They're actually very related to transformers. Transformers are, I'm kind of like giving away the spoiler at the end, but they're a special class of GNNs. But I'll make sure I highlight some of the differences between GNNs and then transformers as we go. We have a few slides. This is kind of like a math-heavy subject. So maybe I should take this chance to advertise the machine learning training course happening with ECM in October. So Matt's very happy. Yeah, so we'd be super happy to have you guys. It's mostly aimed at people from the weather agencies across Europe, so also the member states of ECM and the cooperating states. But we do take people outside of those organizations as well. So I think that the sign-up period's open now. So if you wanna come meet us at ECM in Reading in October, now's a good time to sign up. And then you'll hear about these topics in much more depth. Right. So yeah, coming back to GNNs operate on graph data, so on data that can be represented as a graph. So a graph is just a mathematical abstraction of structured, of weakly structured data that uses something called vertices and edges. So you have vertices or nodes that encode certain data properties and edges that connect two nodes or two vertices that encode relationships between the data. And these relationships can be positional information, distance between two nodes, and so on. So it's a very general data structure that I'm sure everybody who's taken a computer science class has seen before, with a bunch of algorithms that you can define on them and so on. But yeah, so you can define neural networks that operate on data organized as a graph, and this is what I call GNNs for the purpose of this presentation here. So what I'm showing here is basically a simple graph where you have the nodes U's with their own attributes, and then you have the sorry, no, this is the attribute of the graph. This is the attribute of the node, and then this is the attribute. These are the attributes of edges. So you can encode specific information for all of these objects. And the graph attribute could be say like some global property of data encoded as a graph. Let's say if you have a protein, is it a feasible is it a physical is it a good structure for a protein or not? So this could be like a binary indicator. Could this thing exist in real life or not? So this would be like a graph level property. And then the nodes would be the individual building blocks of the protein, and the edges would be the connections between them. Right, so if you think about a graph, an image is also a graph. So it's a very structured graph. So you have these pixels on this nice dog's face that are connected to their neighbors, but the graph is more generally meant to encode unstructured data. So like most GNNs that have been built encode relationships between unstructured data, but you can also use a GNN to process, say, an image. Right. So maybe I should. Yeah, I'm not. Maybe a question for you guys, just to make sure we're all on the same page. What do you think inductive biases, what do you think good examples of inductive biases for GNNs could be? So like, remember you have the data organized as a graph with nodes and edges. What do you think a good inductive bias for a GNN would be? Maybe should I define inductive biases again? These are kind of like assumptions you build into the model to suit the data you have. So the data is organized as a graph. So what do you want these biases to be for GNNs? You want... Yes. Yes, yeah, that's a great example. So you coming back to this. So you have this node here. Basically, it encodes. You've already encoded some relationship with its neighbors. So like, basically, the information propagation should be local. So you shouldn't have like information propagating to faraway nodes that this guy is maybe not even connected to. So locality is one. Another one that might be a good idea to have. Maybe a second example. Yes, yeah, thank you. So coming back to the example with the transformer, you have these positional embeddings. That's because you have, in a sentence, you have a specific ordering of the words, right? But here you have, in this graph, there's no ordering in the in these nodes. So if I label this one 1, 2, 3, 4, 5, and so on, if I look at this guy, which is number 4 in this scheme, When I when I use information from its neighborhood, so from this guy, and this guy, I don't want it to like a priori. I don't want it to know to favor or let's say to be the propagation of information should not be sensitive to the ordering of these nodes. So like if I pull information from this guy, then from this guy, it shouldn't differ from whether the case where I just happen to choose this guy first, and then this guy. See, does that make sense? So you have a permutation equivariance property that you want to have with GNNs, unless there's some information that you encode, such as position, that you want to keep track of, and then you break this permutation invariance by adding positional information in the graph as well. But usually, for unstructured data, you want to be positionally equivariant or permutationally equivariant, actually. Yeah. Okay. So that's that, and then a lot of math on this slide, but it's perhaps unavoidable, or I'm not smart enough to avoid it. Three flavors of the GNNs that you might see in practice. The first are basically just some straightforward extensions of the CNN operation. So instead of having the origin kernel operate on two-dimensional two-dimensional kind of like regions of the image, you have the same operation operating acting on a neighborhood of the graph. So like it's centered on this node here, on the pink node, and it's basically the pink node is exchanging, it's getting information from all of its neighbors with some weights. So XH, the node will update its information based on what it had thus far, and then weighted average of its neighbors. Of course, you can extend that to do an attention-based operation, which is this guy here, this flavor. They're in increasing order of complexity, and the most complex option is the so-called message passing option, where you build a nonlinear function from all the information you have in the neighborhood, both nodes and edges, and you feed this into the MLPs. By the way, these psis and phis, they're just MLP learnable operators that you learn as part of the training process. And this plus, the fancy plus sign, it's just a permutationally equivariant or permutationally invariant aggregation. So you basically pull information from the neighbors, but it shouldn't. The pooling operation should not be sensitive to the ordering of the neighbors. So if you do a sum, then basically it's not. So this is the whole idea of GNNs. Of a GNN layer, let's say. But the important thing is that these MLPs here, they're basically shared by all nodes and edges. So if you first update the nodes, and each update is going to pull information from its neighborhood, and all of these things can be done in parallel using some fancy sparse linear algebra operations. And you can, of course, stack all of these graph GNN layers together and get something like a design pipeline for a GNN model. Go to this blog if you want to learn more about this structure. But basically what you do is the input is a graph, and then you have a sequence of layers that do what I've shown on the previous slide. And at the end of the day, you're left with a bunch of embeddings that you can use for your actual training tasks. So be it classification, be it regression, supervised, unsupervised, you can do anything as long as you have these learn embeddings from the data. Yeah, so coming back maybe by my final question. Yeah, to you, I'll skip the transformers or GNN parts, but why do you think, so just take my word on this, that GNNs are basically a generalization of transformers. But why do you think people haven't abandoned transformers in favor of GNNs? If GNNs are much more general than transformer architectures, and the transformers are basically a fully connected GNN plus a positional embedding, why do you think transformers are still being used and much more so than GNNs? maybe coming back to this. Any ideas? Yeah, there at the back. Well, maybe, but I guess you could. So let's say in this example, you could just make this image of this nice dog puppy to be like a graph of nodes connected this way by edges, and you'd have a graph of this image. Why wouldn't I just forget about transformers and just use a GNN on this image encoded like this? Oh, I can add that. I can add that to the information in the node, like, or the edges. I can add on an edge. I can add information that this edge is like to the left, to the right, up, down. So I can encode that. Yeah, it's kind of like it's almost there. I guess it's the reason is, yes, we do not know why. I mean, the operations happening here in this thing, they're sparsely linear algebra operations. So these are much slower than the fully connect than the matrix multiplies that you have in a transformer. So basically, what you have to do here is basically define somehow extract the neighborhood for each of the graph nodes, which means you have to do a lot of index selection. So let's say for this pixel, I would have to like find the neighbors very quickly and just apply the operation to its 4 neighbors. But that, if I do this with a transformer and I have my image patch that I then flatten, I have this information kind of like in a memory contiguous fashion. So the operations will be much faster because you don't jump around in memory. You don't use any sparse linear algebra operations to like build these neighborhoods. You already have them in the transformer. You already have them as a contiguous memory tensor, essentially. Does that make sense? So it's much faster. You're using different types of linear algebra. You're using full linear algebra versus sparse operations, which the GNNs use. So you're never going to be as fast or as scalable with a GNN as you are with a transformer for two-dimensional images. I don't think, just because they have different layouts, and this is much more amenable to full linear algebra than this guy. Yep. Okay. Yeah. I think this was it. So any final questions at the end? Yep.
I'll throw it. Be careful.
Okay. Also related to your question, so I'm a little bit curious. So could you share on the development of AIFS, why you choose the graph, the GN, not transformer?
So, should I quote Matt again? Do people do stuff that people have shown to work before? So it was the famous Ryan Keisler paper from like a few years ago now. Where he showed you can do a lot of things with just graphs. So, and then actually in AIFS, we switched to a hybrid combination of graphs and transformers. So it's not just pure graphs. We use graphs to embed the data onto the latent space, and then we use something called a transformer to basically process the latent space, and then we use another neural net graph transformer to map from the latent space to the physical space again. So it's a mixture of. We did see for the embedding step, we did see that the graphs are much more efficient than the pure transformers. So our colleague Simon has tested this, and the graphs still do a great job embedding the input sequence and decoding the output sequence. But in between, if you do a transformer as opposed to like a message passing GNN, as people have done, it actually converges much faster. So it's a hybrid option. It's something that we have deviated from as we developed, and again, Simon so that this brought us a large improvement. Yeah.
Ooh, that's a long throw. I'm scared now. I'll try. Good though.
So I want to come back on your comment on graph neural networks versus transformer. Is that the fact that it's better, that transformers are better in terms of computation? Is that just due to the fact that we use graphs that are grids usually, or that are regular in some sense, and then it's not really maybe like representing them as graphs is not maybe the simplest way to...
Yes, yeah, I would say so, yep. So you should always use the fastest method available. And I think in this case, for data that has a lot of structure to it, especially two-dimensional or like tensor structure, as opposed to like a very unstructured graph kind of like data, then transformers are always going to be like faster, computationally faster. So if you work with images, it's always a good shot. Yep.
Oh. I won't give you the challenge of throwing from behind.
Thank you. Okay, so regarding the last question and the question before that, if transformers are faster with structured data and we usually work on mesh grids which are structured, why would you choose graphs? Why would it be more efficient for AIFS to use graphs for embeddings?
So it's just why would it be more efficient for you to actually? So it's efficient in terms of like parameter counts, and it gives better results for the same kind of like the same computation effort if you use graphs just for the embedding step. So it's not like a clear recipe of what you should use for the specific case of AIFS. We have determined that graphs for the embedding step, they work better. But it's not that a pure transformer wouldn't get you kind of like 95% of the way. It's just like it's just a small difference, but it does pay off. Yep. Yep.
Other questions? There's one there.
Thank you. If we come back to your slide 46, so you have a questions about the architecture of neural networks. Because usually we represent a neural network with a lot of circuits that are linked with arrows. Mm-hmm. And but when it comes, for example, to UNet, we represent layers like this. And so this is maybe a very basic question, but do these layers correspond to layers of neurons that are specialized in convolution, for example?
Layers that are specialized in what way?
I don't know. My question is just what is the link between the representations of neural networks that we have, where we have these circles that are linked by arrows, with this type of representation?
Oh, I see. Okay. So I'm not sure if people have seen, or at least as far as I know, I'm not sure if people have looked at the individual, like the meaning, the physical meaning of these latent representations that this network builds. But I would assume that at least in the layers here, you have encoded some information in the image. So if you look at the representations of these guys, you will see something similar to what I've shown on the previous slide with the edges in the images, or like the latent abstract features. But if you look at this, and coming back to AIFS as an example, if you look at the latent representation, the backbone of AIFS, you'd be hard pressed to see any kind of like physical information about the input represented in there. So it's not quite clear how the information is actually embedded. The best way to visualize that would be, please not to me, but if anybody has other ideas, I'd be quite keen to talk to you about it.
So any other questions? What's a latent space? We've been talking about latent space.
Yeah, it's the jargon. Yeah, it's kind of like a let's say a preconditioned, maybe compressed as well, a representation of the input data set. So it's a bunch of layers or model weights that the model learns during the training process, and it encodes kind of like a representation, an abstract representation of the training data set. So like, let's say if you have a bunch of, if you have ERA5 as your training data set, what you can have as a latent space is just a compressed, that is ERA5 on a coarser resolution mesh, but with a higher feature dimensionality. So this would be essentially to like zipping ERA5 into something that's small, and it contains a lot of the original information that was present in your input data set. But yeah, Matt, you want to see you frowning, or no? You disagree? Okay. No, it's just...
All right, and I'll wrap up with one more question. So what's an embedding?
It's to me or to them?
It's to you.
It's just a lookup table. It's just essentially it's a mapping between either an input or a fixed, let's say, vocabulary of tokens for sentence or for language translation to a latent space. So you basically have a lookup table that says, okay, this word or this syllable maps to this representation in an abstract space, in the latent space, and you can use that for learning. Essentially, you can use that to project information from whatever your input space is, or a part of your input space is, onto these bits here. Yep. For continuous variables, you mean? Yeah, I mean, you can have, instead of having a fixed lookup table, you can have like a learnable matrix that maps your input, continuous input, to a latent representation. So it works the same way. Yeah, it's just a matrix multiply essentially, instead of a basic lookup table, which can be thought of as a matrix multiply as well, if you think about it.
All right, thanks so much. So we'll do another convenience break. We'll get here, I would say, shortly before 12. And I think Matt will wrap up the tutorial. And so thanks a lot, Michai.